Good afternoon, everyone. Thank you for joining us for this webinar, which is the first episode of this series of TwinSider Shorts, as we call it. The objective of this series of webinar is to highlight really what was developed in the past 2.5 years of TwinEU, since we are in the final year. Now we have results to show, and this is what we are going to do in this short format of webinar. So today we will start with the Eastern-Mediterranean demo of TwinEU. And for this, we have here the demo leader in Greece, Nikos Koltsaklis, and also the demo leader from Cyprus, Marcos Asprou. So without further ado, I will give the floor now to you, Nikos. And just to mention that at the end of the session, hopefully we will have a couple of minutes, so we will have time for some questions. But Nikos, now the floor is yours. We see you, Nikos. We see the slides, but I think you're muted.
Okay, great. So now you can listen to me.
Yes.
Let's start. So good afternoon, everyone, and thank you very much for joining us today. It is a pleasure to present the Eastern Mediterranean demonstrations developed within the TwinEU project. My name is Nikolaos Koltsaklis from University of Piraeus Research Center. And today, together with my colleague from University of Cyprus, Marcos Asprou, we will present you how digital twins can support electricity system balancing in Mediterranean grids with high renewable energy penetration. I will start with the presentation of the Greek demonstration, focusing on balancing markets, flexibility, and TSO-DSO coordination. And afterwards, Marcos will present the Cypriot one and its specific operational challenges and solutions. Our objective, very briefly, is to explain why balancing is becoming increasingly challenging, how digital twins can support system operators, what we have achieved so far, and which are the next steps for future deployment. Before continuing, I would also like to emphasize that for the case of the Greek demonstration, this is a collective effort developed together with our partners in Greece. So the Greek demo, as mentioned, is led by the University of Piraeus Research Center, or UPRC, but the work has been developed in very close collaboration with IPTO, the Greek transmission system operator, HEDNO, the Greek distribution system operator, NX Group, the Greek Energy Exchange, and RAEE, the Greek Regulatory Authority for Energy, Waste, and Water. So this collaboration between research institutions, system operators, market operators, important for developing realistic and practical digital twin solutions for future electricity systems. So the core concept of the Greek demonstration is the integration of electricity markets and grid operation into a digital twin environment. The digital twin allows us to simulate market operation, balancing services, network constraints, and flexibility activation. This coordination helps operators and stakeholders to evaluate future operational conditions safely before real-time deployment. This slide shows the overall workflow. First, the day-ahead market tool developed by NX creates the day-ahead market schedule. Then the TSO tool developed by IPTO calculates the required reserve needs. After that, the balancing market tool, which has been developed by UPRC, allocates balancing energy and reserves. And finally, the TSO and DSO tools check whether the solution is technically feasible. If any problem appears, feedback is sent back to the balancing market tool until a feasible solution to be reached. This is exactly why the digital twin is important, because future systems are too complex to optimize markets and grids separately. The main objectives of the Greek demonstration are optimal co-optimization of balancing energy and reserve capacity, market-based TSO-DSO coordination, inclusion of new balancing services such as FFR, fast frequency response, and congestion management, utilization of industrial demand response, and support for distributed energy resources integration. So we can say that this work can also contribute for future policy and regulatory discussions. The tested system is not the existing one, but the future Greek system of 2030. So starting from the market layer, the day-ahead market simulator, the colleagues from HENEX have completed the 2030 Greek market order book based on the official guidelines such as the National Energy Climate Plan and the 10-year Network Development Plan. They have integrated the Attica-Crete interconnection, battery storage integration in the island of Crete, and dispatchable renewable energy modeling. So to validate this day-ahead market environment, we have applied a stress test case scenario for an Easter Monday of 2030, and we compare it with an Easter Monday of today market operation. This is a challenging operating condition characterized by low demand and very high renewable generation. So here we can see that on the buy side, we observe stronger exports and higher battery participation compared with the baseline case. So this already shows one important conclusion, that is, future systems with high renewable penetration will require significantly higher flexibility support. On the sell side, the results verify the same trend. Renewable energy and battery storage clear more energy compared with the baseline case. So we can say that both buy and sell sides indicate that storage and flexibility become key elements of the future market operation. Here, the market indicators make the impact even more clear. So in the 2030 case, low price periods become longer, and negative net load periods become deeper due to the more significant high renewable penetration. The average market price decreases while social welfare improves. So we can say higher renewable penetration improves welfare and increases also market activity, as we can see here. But at the same time, it creates stronger balancing and operational challenges for the system. So this naturally leads to the next step in order to calculate the reserve requirements required to operate such a system in a secure way. For these reasons, in this slide, the dumb results are then used by the HYPTO reserve calculation tool. So using the day-ahead market schedules together with updated renewable and demand forecasts, this tool calculates reserve needs for every market time unit in both upward and downward directions. So here you can see the calculated reserve requirements for the 2030 scenarios. These reserve values are then used directly as inputs for the balancing market optimization. Once the reserve market requirements are defined, the balancing market simulator implements co-optimization of those services, balancing energy and the respective reserves, and allocates those services across technologies. So we can see here that how natural gas, hydroelectric units, battery storage, and industrial demand response contribute to those balancing and reserve services. Battery storage becomes especially important, as you can see, for fast flexibility and congestion management services. This becomes even more clear in the dominant technology analysis. So here, hydro dominates several upward services. Natural gas remains important for balancing and frequency control, while battery storage dominates fast response and DSO, congestion management services. However, market optimal schedules alone are not sufficient. So the natural next step is to verify whether these market schedules are physically feasible from the grid viewpoint. For this reason, transmission grid feasibility is checked after the balancing market schedule has been created. For that reason, the selected validation area in that case is the grid transmission system, including all the planned 2030 upgrades with high renewable penetration and the battery storage units placement. So power flow simulations verify whether the balancing market solution is physically feasible for the grid. At the same time, the next layer is the DSO feasibility validator, which has been implemented by HEDNO. So its role is to check whether battery set points can be safely applied on the representative medium voltage feeder without violating local grid limits. So this specific tool checks voltage levels and equipment loading and returns as a feedback specific decisions related to accept or curtail or reject that specific schedule. This is very important because in the 2030 future system, many resources will be connected at the distribution level and not only at the transmission one. So in this slide, you can see some representative corrective actions. So the main corrections include the reduction of battery charging during low voltage periods, or the shifting of charging to periods with more voltage margins, while discharge is implemented when and where it can support the grid. We can say that as a final synopsis, the grid demonstration has successfully developed an integrated day-ahead market balancing market digital twin with TSO-DSO feasibility validation of the market schedules. So the work also demonstrated the integration of additional reserve services, such as congestion management at both TSO and DSO sites, and fast frequency response services. The simulations in general, we can say, improve observability, controllability, and evaluation of future electricity system operation under realistic conditions, since we said that the test case is a 2030 Greek power system. And as a final conclusion, digital twins prove to be valuable tools for testing future electricity market and grid interactions before real deployment. The work demonstrated the importance of integrating market simulations, flexibility activation, and network validation. Next steps include the examination of additional stress test scenarios. For example, here we have mentioned some of them: spring weekends with severe solar overgeneration, so combining low demand with significant renewable generation, and steep evening ramps after solar sunset. There is also another ongoing activity which is related to the integration of the Greek and Cypriot day-ahead markets, formulating a pan-European scenario. If there is any clarification needed or any question related to that, my colleague from HENEX can provide some additional information and clarification regarding this activity. That's all from my side. Thank you very much for your attention. I will now give the floor to my colleague Marcos for the presentation of the Cypriot demonstration.
Thank you very much, Nikos. I'm not sure if we're going to take questions now or later. Another round.
You can go ahead now, Marcos, and
Okay.
let's see the questions at the very end.
Okay, let me share my screen. Let me know if you can see my screen or not.
Yes, perfectly.
Okay. So many thanks, first of all of you that you are with us and give us the opportunity to present the work that is done in TwinEU and in particular in the Eastern Mediterranean demonstration. As Nikos mentioned, this demonstration is currently separated in two, let's say, regions, the Greek region and the Cypriot region. So in this short presentation, I'm going to present an overview of what is done in the Cypriot power system digital twin demonstration that both myself and my colleague Leonos Hadjidimitriou are leading. Just to mention that my name is Marcos Asprou and I am a research lecturer at the TO Center of Excellence of the University of Cyprus. So the Cypriot power system digital twin is a collective effort of Cypriot partners, mainly from the we have with us the Cypriot and distribution system operator, the Cypriot transmission system operator. We have with us Syntex Solutions for facilitating the development of the different tools that are involved in the Cypriot demonstration, and we have also with us Aeolian Dynamics, which is a wind power plant owner and participant in the market. The focus of the Cypriot demonstration is twofold. The first one we would like to examine and stress the importance of the interconnection and the importance of having a digital twin interconnection system of the Cyprus power system with the Crete and mainland and the Greek mainland power system in the sense to support the frequency of the Cypriot power system. And of course, we would like to also to see examine some challenges related to the Cypriot distribution power system. That's why we have developed also a task related to the Cypriot digital twin to examine the congestion and voltage management aspects under future scenarios, but also to stress the importance of cybersecurity in such systems. The activities of the Cypriot power system digital twin are separated in two tasks in the TwinEU project, in task 5.3 and task 5.6. So you can go and see more details in the respective tasks if you want. So starting with the first approach, with the digital twin architecture of the distribution grid, as I said, the main objective was to stress and test several congestion and voltage management solutions for future distribution grids that experience high penetration of renewable energy sources. This is the main architecture that we have developed in order to examine these solutions. This digital twin architecture has a data layer where it manages the information transfer from the outside work, meaning the distribution grid, the actual distribution grid, to the digital twin. We have the simulation layer where we have developed a digital twin distribution grid in a real-time simulator. We have the control layer, which is integrated as a hardware-in-the-loop approach to the digital twin, and this controller actually provides it's mainly the brain of the system controlling the distribution grid operation. We have the communication layer where you can see it in the graph here, where you can see the middleware for data exchange between the hardware in the loop controller and the distribution grid power system with the digital twin. And in this layer here, we have performed some cyber attacks. And we have lastly the visualization layer where we can see the operation of the system and some other information related to the power system operation. So the main objectives here for this architecture, for this digital twin architecture, is to perform operational and cybersecurity scenarios and assess the impact of these scenarios to the grid operation. So related to the scenarios that we have developed in this task and in this aspect of the digital twin, we have operational scenarios, meaning that we examine several stress tests for the congestion management of the power system in case of high demand, high power demand and high penetration of renewable energy sources. And also we have, as I mentioned, some cybersecurity scenarios, just to stress the importance of having cybersecurity measures in future distribution grids, where we are going to have several control and monitoring capabilities. These cybersecurity scenarios mainly concentrated on the force data injections and measurement sampling. So let me give you some indicative results for the cases that we have run for both scenarios. These are indicative results, and more information can be found to the deliverable 5.2 of the project. So you can go and see more in detail results. So in these results, we have this, we assume that these distribution grids. This is a representative distribution grid of the Cyprus power system. And we have the objective, we have deployed some controllers that deals with the voltage and congestion management. This is objective function. I'm not going to go into detail, but this objective function mainly tries to minimize the cost required by activating ancillary services for managing the voltage and the congestion of the power system. And here is an indicative result where we have two cases. The first one with the red line is the case where we don't have any control capabilities to the system. This is the blue curve with the dashed line. So we don't have any congestion management capabilities, and you can see here that at the noon hours where we have high penetration of renewable energy sources, and this is something very, very common in Cyprus power system due to the high radiation that we experience. You can see that there is a congestion issue in the transformer at the beginning of the feeder. So and with the control capabilities that we have, and we control flexible resources and also battery energy storage systems, you can see that we maintain the limit of the loading conditions. This is another results, mainly for the voltage now. As you can see again, this is the voltage before the control actions, and this is the voltage with the control actions. In all the cases, this is some indicative voltages from the distribution grid. In all the cases, we managed with the control capabilities, with the controllers that we have developed to maintain the voltage within the limits. But in some cases, like this one here, you can see that the voltage without any control capabilities, you can see that the voltage goes beyond the operational limits, the acceptable limits. And this is the response of some flexible resources, such as the batteries, when they charge or discharge according to the set points that the power system, the controllers send to the flexible resources. So moving on to the cyber attack scenarios, we have performed two types of attacks. One is the force data injection, and the other is the measurement tampering. This is the case of the measurement tampering, where we assume that the attacker can gain access to the substation of the feeder and it tampers the power measurements of the substation that are received by the controllers. As you can see here, when this is the case where we have an attacked measurement, and this is the real, let's say, case of the power in the substation. As you can see, with this cyber attack, the voltage, although the controller is activated due to the erroneous measurements from the cyber attack, you can see that the loading conditions are exceeded due to this operation. And this is another scenario where the attacker accesses the set point of a battery. So instead of charging, or instead of discharging, the battery is charging, and then you can see the effect that is also experienced at the substation level, where you can see that you can see a peak here where the inverse set point of the battery is applied. So it's important here to stress that the cybersecurity measures is also important in the distribution grids instead of apart from the control actions that are made. So moving on to the 7.6 task, the HVDC interconnection digital twin. The overall concept here is to develop a modular digital twin for the Cyprus, Crete, and Greece power systems. We would like to see it from the transmission level now. In 5.3, we see in the distribution level. Now we are seeing the Cyprus digital twin from the transmission level. So we have developed this modular digital twin at the transmission level. And we have also developed, apart from the digital twin, we have also developed a regional coordination to manage the frequency containment reserve and frequency sensitivity mode support that is provided by the HVDC. The current situation now for the Cyprus power system is that it's an islanded power system, and it's envisioned to be connected to the Crete and then Greece mainland through an HVDC interconnection. So this is the digital twin architecture that we have developed. At this part of the right part of the screen, you can see the real-time digital simulation where we simulate the three main systems involved in this HVDC connection in the real-time simulator. We have a monitoring, we have embedded middleware that facilitates the data exchange between the digital twin and the monitor and web-based management interface. And we have also some data imported to the digital twin through some APIs and some live and historical configurations that we have in the sites. So for instance, the TSO and the Eolian Dynamics and the IC. So this is details about the middleware. As I said, we have imported data from the three TSOs and DSOs, and this is the regional coordination for frequency support. This is a concept. Actually, the TSO imports the requirement for the inertia and the FCR, and according to the real-time operation of the system, the gains for the FCR and the FSM are determined through this coordination scheme, and the power that should be provided by the HVDC in order to support the grid under a frequency band is determined through this condition. And this is just an indicative result. This is where the support is deactivated by the HVDC. You can see here under the disturbance, the frequency at the Cyprus case is 49.42 Hertz. But with the support activated, with the HVDC activation, the frequency is around 49.63. So there is an improvement in the frequency response due to this HVDC support. And then the conclusions, of course, digital twins are needed in order to have a non-invasive and realistic environment to tune and manage new solutions. And this is quite important for research and innovation activities. We can also investigate several extreme scenarios and help with the decision making of the operators. Progress so far, we have developed digital twins for both transmission and distribution grids. We have developed several scenarios for congestion, cyber attacks, and also regional coordination, assuming that Cyprus is interconnected with the Greek power systems. And as next steps, we are finalizing our activities through gathering the signal, gathering the necessary results, and finalize the twin deliverables for the TwinEU. That's all from my side. Thank you very much.
Thank you very much indeed, Nikos, and also to you, Marcos, for these presentations. It's really great to see, how these demos are taking or took shape in this period within the TwinEU. We are running a little bit late, but still, I think we can stay for one question, maybe, if there is anything from the audience. If there are no questions, then maybe I can say just two other things. One is that we are going to share both the video and the presentations on the TwinEU channels, so you will be able to find everything that was presented today. And also, please keep in mind that the next episode is coming in 2 weeks' time on with the Dutch and French demos of TwinEU. So thank you very much for your attention and for the presentations, Marcos and Nikos. And stay with us or connect with us for the upcoming sessions too. Thank you, and wish you a nice day.
Thank you very much. Have a good day. Bye.